Greetings, this is Greg. I'm going to make a quick video here about the Euro compulsion intercooler system. I think you folks may find it interesting. I'm just going to show in a video how effective the system is. As you can see, this car is equipped with our V4 intake, and not sure how well you'll be able to see it here. Oh yeah, you can see it okay. There's the intercooler. The piping is, of course, all buried down in there, but it's silicone piping for reasons which I'll explain. Let's talk for a moment about silicone as used in automotive intake and intercooling systems. There's a lot of confusion about this. The reason we use silicone is that it results in cooler air reaching the combustion chambers, thus it's safer in high boost applications. In physics, there's a property of materials called thermal conductivity. Thermal conductivity is defined in part as the quantity of heat transmitted through a unit thickness of material. In other words, thermal conductivity is a measurement of how easily heat passes through a material. Heat passes through some things, aluminum for example, very easily. That's the reason radiator and intercooler cores are usually made out of aluminum. Aluminum allows the heat from engine coolant or charge air to pass through easily and then be carried away by the airflow at the front of the car. If you made a radiator core out of a material with low thermal conductivity, like plastic or stainless steel, it would not work very well. With an automotive intake system, we have the opposite issue. The air coming into the intake is already at or near ambient temperature. We want to keep it that way all the way to the turbo. Since the tubing needs to pass through the hot engine compartment, we need a material that's going to keep engine bay heat out. Aluminum tubing is tempting to use here because of its low cost and it's easy to use in manufacturing, and it can be coated in any color or finish you want, but it's just the wrong material to use in these applications from a technical standpoint. Aluminum has a thermal conductivity number of 205. For example, steel is much lower at 43 and stainless steel is 16. Silicone is much lower at only 0.13, so not only is the thermal conduct of silicone much lower than aluminum at 0.13 versus 205, but we use tubing that's far thicker than any typical aluminum tubing used in an intake system or intercooler piping. We use 5 layers of silicone and 4 layers of Kevlar reinforcement. Once the air leaves the turbo, and especially after it leaves the intercooler, we don't want to expose it to engine bay heat any more than necessary. I don't understand why so many people go through all the trouble to put in an upgraded intercooler only to run the air through a hot metal pipe on the way to the intake manifold. No auto manufacturer does that. They either use silicone, rubber, or plastic, or more often than not, a combination of those three. But all of those are materials with a very low heat transfer number. All of the intake and intercooling systems designed in my shop use reinforced thick silicone for the tubing. In the case of the car in this video, it's running a Euro compulsion V4 intake and intercooler system. My car has a boost gauge and an air temperature gauge with the sensor located just after the intercooler. Both of these are from VaitrixUSA.com. So let's hop in and see how well all this theory works in actual practice. Please keep in mind it's tough for me to video and talk at the same time, so the quality of this production may not be too good. We're continuing on the road. We're not going very fast, only about 30 miles an hour. But we still have enough RPM to make plenty of boost here. The intercooler obviously works better the faster you go, since it's a front-mounted air-to-air type. But that means that this is really a good test of the intercooler's effectiveness, low speed and with some boost. I can't go to full boost, unfortunately, because I don't want it to trigger the water injection, which will skew the results. But you can see we'll add a little bit of boost here, do it a few times. You may be able to hear the blow-off valve triggering a few times. That's the Forge Atmo type. And take a look at the temperature gauge. Essentially no change. We'll put it on boost again here. Now the faster we go, like I say, the more effective the intercooler is going to be, and those temps will actually drop just a little bit. But the overall point here is that the Euro compulsion intercooler holds the post-intercooler temps amazingly close to ambient. This particular gauge, which is the Vaitrix temperature gauge, has a alarm which can be set. I've set mine for 120 degrees Fahrenheit, at which point a light goes off and it makes a beep. And I've never seen it reach that, even on 100-degree days, at low speeds, on the boost all the time. It never reaches that number. So I'm extremely happy with how effective our intercooler system is, and I just wanted to share that with you folks. Hope you're having a good day. Thanks. Goodbye. I've been driving for a little while. I've been on and off boost quite a bit. Now I'm pulling into this neighborhood. I'm going to find a spot here to come to a stop, not in the shade. There we go. It's a nice spot. Now, you can see car's still fully warmed up, still 92 degrees outside, and intercooler air temperature is still right there at about 92 degrees. Now, as we sit still, everything will warm up. This is due to heat rising off of the radiator and getting into the air intake system before it even gets to the turbo. All of the piping in the turbo, the piping that leads to the turbo for the air intake, will absorb a lot of heat and start to warm up. The intercooler piping will do the same thing. And the intercooler is not getting any fresh air through it. So the longer we sit here, the more the intercooler temps will warm up. And, well, it's kind of like watching grass grow. You can't see the needle move, but you might just have to take my word for it. If we sit here for 5 minutes or so, or maybe a little bit longer, that temperature will rise probably about 10 degrees, maybe even 15 degrees. So it will slowly creep up, and then because of all those things being heat soaked, it takes a surprising amount of distance to cool back down. But it happens faster with this system than with most others. I'd say within about a mile of driving, it'll fully cool down. But again, notice how slowly it's rising. Anywhere I drive, the light would have turned green by now, so that's about all the heat soak you're going to encounter with this system in real life. So that's all I have to say about this particular system. I hope you guys enjoyed this video, and thanks for watching, and have a good day.